Excellent. Hey, Sebastian. All right, so it looks like just you and me so far. We'll see if anybody else joins in. But starting off, we're going to have no lab today. We'll complete it next week, and we should be just fine. It was on colligative properties, which you can get outside by going out and throwing some ice on the snow or some salt on the snow. All right, uh, so that's not too big a deal. I do want to go ahead and show you see if I, all right, there it goes. I'm not sure if we did this was practice quiz 10, but I think it was out of order. We didn't actually do it. So I'm gonna go ahead and start on that one. I don't think we actually did that. I lost my chat here. Um, all right. Well, if you need to stop me, just stop me. I don't seem to have chat anymore. All right. So this reaction going only in one direction. We'll talk next week about reactions going in both directions. So it's a slightly different arrow. But this reaction is going in one direction, and it asks us what products are produced the fastest. And one of the things that we want to pay attention to is these coefficients. And the coefficient here for the reactants isn't as important for this question, but they may ask it later. So one thing we said we can do is do 1 over this rate equals 1 over 1 for the next one equals 1 over 6 for the next one. So, but it's a little confusing because we still are having the H2 form 6 times as fast as this. So this rate is equal to 1/6 of that rate. In other words, this one, the H2 reaction, that part is forming 6 times faster. And so when they want to explain that choice, we refer back to the coefficients. Let's see if it'll let me scroll down. There it goes. And so then when it asks me for the rate of pH3 in terms of the rate of H2, then I'm still going to be using my 1/4, and I'm going to use this one as X and this one is Y just to make my drawing a little easier. So 1/4 equals 1/6 the rate of this. So this is usually written out as rate, exactly as it says there, rate of H2. All right, so they want this X in terms of Y, and so this will be 1/4 times 6, and that'll equal Y. So the 6 will cancel out here. So this will be 3/4, which is 1.5. Oh, and we still have our X. X equals Y. Okay. We could take it the other way, and if they wanted the X, we could bring it in, and X would be 4/6 times Y, which would be 2/3. 0.6. Okay. So it's all a matter of which one they're asking for. So they want this rate in terms of that. They're probably looking for this 0.6. Okay. So you have to be careful on these. That's the hardest part is deciding which one they want to be in terms of the other one. So in this one, they want this X. So we'll make that X, and this will be Z. And so this is our P4. And so P4 was 1. And so they had we have 1/4 equal, that is my ability, 1/4 x equals 1/1 z. And so easiest terms would be to say that that rate of pH 3 is equal to 4 times the rate of the z, which is the P4. And then they asked for us to do the rate of H2. So because we went ahead and wrote all these, up, because we went ahead and wrote all these out, it actually works out pretty easy. So uh, the H2 is what they want. So that's that. And here's this. So H2 is 6 times that one. So this rate of H2 will be equal to, since it was 1/6 and this was 1/1, then we can say this rate equals 6 times this rate. Okay. And then so that's that one. It's not too bad. So that's practice quiz 10. So looking at, we did 11 and 12. So I want to introduce us. Well, we did 11, which had the rates. 12, I'm going to do it slightly different way. So 12 is, oh, sorry, this is chapter 12. We do make sure we did number 12. Working. We did 12, 11 and 12. Uh, so I want to show us how to do some stuff in Excel. For instance, this well, let's just do practice quiz 13. It's probably the easiest way of doing this. So practice quiz 13, they said they did this reaction and they said it was second order. And one of the things that we want to make sure is that we do the after experiments, before experiments, and then the integrated rate law. And so all that comes from this. So we're doing second order. We're going to be doing this information. Okay. And so we really only have to graph 1/A versus t. So I'm going to go ahead and graph that in Excel real fast. And I'm just going to highlight this and I can hit copy. And I'm just going to paste that over here. So the next thing I have to do is it said 1 over, see if I get to where my stuff is. 1 over the concentration versus time. So I'm going to go ahead and make this one 1 over concentration. And this will just be 1 divided by whatever this one was, B2. So it makes it nice and easy to fill in this table without having to type all that into my calculator. And so I'm gonna go ahead and insert while I'm here. I'm gonna highlight this and I don't want to do it. Okay, there we go. And insert an XY scatter for this, so 1 over concentration. And the main thing we're after here is actually the trend line being linear. And this isn't going to show it until it's over there. So I'm going to format this trend line. And I need to make sure I have my equation in R squared. So R squared is really good here at 0.99. So they told us it was second order. We already kind of knew that. But we now have this y equals 0.0612 plus 99.368. Okay, so that is my values for my equation. So when I have to do it over here, I'm going to go ahead and write this out. y equals 0.0612 x plus 99.368. And that'll allow me to find, so the slope is k. So that means my k will be that 0.0612. And the half time will be 1/2 times 1 divided by k0. And k0 is, I'm sorry, the initial absorption is zero point zero 0.01. We could also use the 1 over 99.368, which will be just about 0.01. So when it asks us to do these things, so before let me get us a text box, or I could just draw it here. Yep, right here. Before the equation, we knew it was K times our C4H6 to the n power. I'm gonna just place that to the n power. So that was before we did any experiment. Then they said after the non-integrated after experiments, so they told us that was going to be to the second power. I keep hitting that wrong one. There we go. And then they wanted the integrated rate law. And so the integrated rate law, we said we can find off of this table. And I'm going to just pull this over. And the integrated rate law says 1 over that concentration of A, which is the C4H6, equals our KT, which our K was 0.0612 times T. We're just going to do parentheses T plus 1 over, in this case, it's 1 over the initial, so that's 0.01. So that would be our integrated rate law. And then they wanted us to find the slope. And so our slope was 0.0612. And then they ask us to figure out when does the concentration come out to be 0.00295. And we could come to Excel and Alt tab. I could come to Excel and come over here and find when this comes. But instead, since we have the equation, we have the integrated rate law, we're just going to plug that in. And so, there. So we're just going to plug this in. When does it become 0.00295? So that's our concentration. So when we wrote this out, using the integrated rate law, it was trying to think, did I write it in the right place here? It's here. 1 over our concentration. So 1 over 0.20295 equals, and then we know that our equation then was 0.612, 0612, sorry, times T plus 1 over 0.01. And we're just going to solve that for our T. So let's see, I'll just do that over here in Excel real quick. So that's the 1 divided by 0.00296. Oh, should have been 295. Anyway, let's go ahead and make that 295. 338.9. Okay. And then I'm going to take that number and I'm going to subtract 1 divided by 0.01. And that gives me 238. 1 over 0.01 should be 100. So that makes sense. And then I'm going to take that number and divide it by the 0.0612. And so my time being 3,904 seconds. And when I look at 3,900, that's right in here. And we're looking for it to be 1 over that concentration. And so if I come, this one's hard to see, so I'm going to come over here to the data, and 1 over that concentration comes out. So when the concentration is actually 0.00295, it is somewhere between 3,600 and 4,400, right? And so that puts us right about where our data should be. So right in that. So if I just did, yep, 1 divided by 0.00295, 338. So I'm looking for where this comes across at 338, and it should cross right in here at our 3,900. So this number looks really big, but this should be 3,904. We're just going to call it 3,905 seconds. It looks really big. Keep in mind it's in seconds, and it matches our data. So this reaction takes a little while to get there. Then it asks for the first half-life and the second half-life. So since this is second order, I'm going to come over to my table. And half-life is given as 1 over K times the initial. And so when I'm doing this, the one then, so T here, 1 over, and then make sure you use parentheses for this. So 0.0612 times, my initial was 0.01. And I'm taking that from this time here. And so I'll go ahead and stick that into Excel real fast, get the info for it. So equals 1 divided by 0.0612 times 0.01. 1633 should be half of the concentration. Okay, and then we're going to double check our data and kind of see if that makes any sense. So half, we start at 0.01, so half the concentration would be 0.005. So 0.005 happens close to 1800, but partway between 1,000 and 1,800 seconds. And we got 1633, so which is closer to the 1,800. So that makes sense. That's where it's halfway. But we now know that this comes out to be, and we said 16, well, we'll call it 1634 seconds. And then for it to be the half-life again, one way we can do this is we want the second half-life. So the second half-life will be 1 divided by our 0.0612 times, and we want where it's at already at half. And so our half concentration was 0.005, and we'll just use that as the new initial. We'll use that as the new initial. And so I could certainly type that in as being 1 divided by 0.0612 times 0.005. And it says that's going to take 3268. And that should get us at half of 0.05, which should be 0.0025. And that is, let's see. So 0.005 was here. And then notice here we get a kind of a jump. Okay. Um, Another thing that we can certainly do is we could have just said it takes twice as long. So this half-life was 1634. And then if I double that, I actually get my 3268. So I'm just going to multiply this by twice the time. And that gets me to my half-life for second order. That works. But we can always just plug in our initial concentration, our final concentration times our initial concentration. And that'll give us the second half-life. But I'm going to go ahead and predict the third half-life will be 3 times this one. Or, I'm sorry, even better, it's 2 times this one. So it'd be 64. Uh, oh man, I'm gonna have to 66. 36. Okay. Then they asked down here, what is the concentration after of the reactant after this amount of time? So we're still using this same equation, 1 divided by 0.00, 1 divided by time. So, or 1 divided by the concentration. So we'll make that our x. 0.00610612 times the time here is 6534. Now, 6534, hey, that looks about like this half-life, so it should be half of that. And they said 1 plus the so our equation was 1 where's our rate law right now? Right here. Plus 1 over 1.01. 1 over 0.01. And so we're just solving for 1 over x. So the easiest way to do this was to solve the right-hand side. Okay. They wanted to add a multiplication sign there, but okay. So 499.8808. Now that's 1 over x. So this is still 1 divided by x. So I'm going to do the inverse of both sides. So x would be 1 divided by this number. I got 0.002. And that should be my concentration after that amount of time, 6534, 0.002 molar. And 6534 is down past here, but we can see 002. So it should be in about that range. So when you're doing these, always double check. You want to make sure that when you go back to your data, that it actually makes sense, because it's real easy on these to make a typo or to forget a parentheses or something like that. So I'm going to go through and just kind of make sure it makes sense that when we were at half the concentration, so we started at 0.01, that it made sense that the concentration, the time would be in here. and then we're at half that again. And so it made sense that that would be in here. This 32 looks a little wonky. Let me double check that value. That looks fine. Um, and then we just plugged this in and did the algebra to find that, but it matches our data. It's going to take uh after 6534, we're going to have less than this. That concentration is going down. And so it does, in fact, work. Now, remember, this is not linear. This part is not linear because this is our linear one, which was 1 over the concentration. So had this one been linear, it would have been first order. So we're getting the approximate ranges, but this will not match our data perfectly in terms of a straight line. So you can't just say halfway between these is this, because this is going to give us a curved line. And this is the one that gives us the straight. So what we could do is if I wanted 1 over, if I wanted to come out to that time, 60, what was it? 6534. So I'd come out right over here, and let's say that's right around 500. And so, but I do have to do 1 divided by the 500. And that gives me that 0.002 that we found. Okay, so don't forget to do this one. The values on the Y, you have to actually do 1 over the concentration. Yeah. Any questions on that one? Nope. Okay, good. So 13's not too bad. Like I say, Excel actually helps out a lot with that. Um, the rest of them are kind of based off of, oh, let me get to our notes here. Here we go. Are actually based off of, this is gonna walk us through how to do it. This idea for doing the reaction coordinates. And so this bottom part is called the reaction coordinates. And so on the left-hand side, I've got the reactants. On the right-hand side, I've got the products. Energy is going up. So usually we think in terms of enthalpy going up. I don't know. I guess it fades into blue. Crazy pen. Um, and so there's a couple different parts that we want to make sure we kind of figure out. So here's my reactants, and they're proceeding over here to my product. So this is A plus B going to C plus D. And so we want to be able to tell a couple of things by looking at this graph. First off, the reaction, this is the enthalpy. This is the amount of energy trapped in the bond. And so this is saying that we need, as the reaction goes, we need extra energy to get that to start. And then when we end up at lower energy than we started. And so overall, if I do my products minus my reactants, this side is lower than this side. So this will give me a negative delta H. So if I do the final minus the initial, that's my delta. And so that gives me a negative delta H. That means there is less energy trapped in the bonds. And it had to go somewhere. And so where it went out to the system. And so this will be exothermic. And so the energy gets released by this overall. Now, this is our energy of activation. This is what it takes to get the reaction to go. And everything has some positive energy of activation, even in this case where we get more energy out than we put in. But there's some amount of energy needed to get the reaction to start. Okay. And so a bunch of things affect the rate, and we can predict them here. And one of the main things is the size of this energy of activation. And so it's the taller this hill, the harder it is to go over. And if we can lower the energy of activation, this reaction would go faster. And so what we actually do is we can lower it by adding a catalyst right here.
Will that be like temperature
Uh,
or?
temperature makes the reaction go faster because we have more energy to get over the hill. And so if the lower temperature we are, the harder it is to get over the hill. But a catalyst, what it does is it lowers this energy of activation. And so it speeds up the reaction even at the same temperature. And so if I raise the temperature, I'm overall going to raise the speed, but it's going to also affect this catalyst version as well. And so a catalyst just allows us to go around this hill instead of going over the hill. In other words, it makes the hill get smaller. Now, even if I was going, okay, I guess I can't go over there. Even if I was going uphill, it still has this energy of activation. Okay. So uh, a catalyst is not a reactant. It's not a product. All it does is lower this energy of activation, make the reaction go faster. There's an opposite of that that makes it bigger, and that's called an inhibitor. And it's just like it sounds, it makes the reaction go less. It causes this energy of activation to be higher, and it slows the reaction down. So an inhibitor, same role as a catalyst, it just does the opposite. It makes it go slower. All right. So this would be go ahead.
I was going to say, what would be an example of a catalyst
Okay,
and an
great.
inhibitor?
Yeah, so a catalyst, the one of the more common ones is in our cars. The exhaust that comes out is not really completely carbon dioxide and water. What we usually get is a bunch of side products that are uh, some fairly long chain alkanes, some carbon hydrogen chains. And then in our catalytic converter, there's all these different metals and they have real sharp kind of surfaces like this. And as the hot gases from our exhaust flow over them, they kind of stick to the surface and they get bent on these sharp edges. And this is on the atomic scale. And then all the heat causes those to go ahead and react with oxygen even more. And so what's coming out of the tailpipe is less of this big pollutant. So if you ever see like a school bus or a car that doesn't have a catalytic converter, it's a big black cloud coming out the back. When you put this on, it helps to get it reduced down to a lot smaller hydrocarbons so it doesn't make that big nasty stuff. Most of it burns. And so that's a catalyst. Another thing we can use, trying to think of another example we use. There's all kinds of ones that we can use. For instance, if I just have a surface of platinum and I'm trying to react hydrogen gas with, uh, and I'm gonna just do a carbon-carbon double bond. That these two gases, so if I put this with, well, it'll never come back. If I put that with, I'm gonna just, there's two hydrogens on each of these. We don't need drum, but if I put that together, they don't want to react very well. But if I have this platinum surface, they both bind to that. And I probably have a pretty picture down here somewhere of this. Let's see. Nope, I don't. It's in the book. But saving it for class. Um, but they bind onto this surface. So these the carbons kind of the double bond gets attracted to this platinum. Palladium and nickel will do the same thing. And then the hydrogens kind of separate from each other and they bind to the surface as well. And so even though I do these in gas form, they stick to the surface. And now everything's kind of two-dimensional. This hydrogen can zip in and it hits this side. And now I have this one that has three hydrogens on it. And I still have this hydrogen over here. And now that opens this side up to where another one of these hydrogens can bang into it real fast. It's already kind of lined up. And so we end up with a carbon. Yeah. Each carbon gains a hydrogen. And so this reaction is very useful for us to get rid of double bonds, but it doesn't want to work in the gas phase. But once I have this CH3, it doesn't want to stick to the platinum anymore. And it just kind of blows off and we collect it as a product. And then now my platinum is still empty. It's lost all that stuff that stuck to it. So more stuff can stick to it and it can go again. And so that's the key is it doesn't get used up. It's not a reactant. It's not getting used up and it's not being made. So a lot of times what we say is it gets used, then remade. And that's what's going to be key about a catalyst is it gets used up at first and then it gets remade. So it's there at the beginning, there at the end. Another thing we'll see happen sometimes is what we call an intermediate. See if it'll let me just type. I'm gonna type that term first. And then intermediate is kind of when we have a two-step reaction. A nice way to think of it is the product of the first reaction, and it'll be the reactant of the second. In other words, it gets made, then used. So it won't be there at the beginning, it won't be there at the end. Whereas a catalyst, we said it gets used, then made. And so those two are real easily confused. So if I was drawing out my beautiful pictures here, so reactants, products, energy, or H. So if I'm looking at a two-step one, it'll have a little hump in the middle, and this is the intermediate. And so it doesn't really affect anything in terms of this delta H. It's just it gets made. We can actually collect it. I can put it in a bottle for the most part, and then I could do the second part of the reaction. So sometimes we collect it and then we do a separate reaction. Sometimes we do it all in one pot. It's kind of like cooking. Sometimes you cook things in different pots and then combine them. And then other times you cook everything all in one big pot like you were making soup or something. Okay. And so each one of these has an energy of activation. So that would be the height from here to there. And then this one would be from here to there. And then each one also has a delta H. And so that's this height. And then that would be this height. Okay. But overall, there's a delta H for the whole process. And we would just set. So this one's going uphill. So if it's going uphill, it'll have a positive delta H. And that means it's endothermic. And so, but a catalyst lowers the hills, and an intermediate is this temporary product. It gets made, then it gets used up. We do have what we call the transition states. They're here, and this is where the bonds are halfway made, halfway broken, and they get the problem with those is we cannot collect them. All right, they're just so if we stop the reaction, it'll collapse one way or the other. It doesn't want to be at this high energy peak. But by making changes to this, that's what the catalyst mostly affects, is what this transition state looks like. So we saw before where we had it on a surface and it sped up, got everything lined up. Other things that affect the transition state are going to be stuff like big bulky groups get in the way. How fast things are going. You said temperature, so that will definitely affect the rate. We'll also see an effect of, we saw the effects of concentration. And then another thing that really affects us is the state. Oh, I guess I drew a heart. I love this stuff, I guess. All right. A gas is way, way, way faster than a liquid. And that is way, 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 way faster than a solid. And so if we can do things in the gas phase, it's really efficient for us. The reaction goes fast. If we do things in liquid phase, so that's why when we have a lot of things going on in a solid, we tend to try and dissolve them and do them aqueous. And so that's why most of the reactions that we study in lab turn out to be aqueous so that we can speed up the reaction. Okay. All right. I think that's good for today, unless you got any more questions.
Again, thank you for everything.
Uh-huh. All right. So have a great weekend. Like I said, we'll do the lab. We're going to combine it with next week's and kind of work from there. All right.
Have a good day.
You
God
too.
bless you.